This paper studies a curious phenomenon in LLMs, where attention heads focus heavily on the first token in a sequence, usually the beginning of sequence or token. The authors note that while many previous works have studied how to use or avoid this behavior, few have explored why models develop these patterns naturally during training. They frame this as understanding why gradient descent consistently produces this behavior without explicit programming. The key insight is that attention sinks aren't a bug, but a useful feature for information processing. Figure 1 illustrates how attention sinks help control information flow. The diagrams compare cases with and without a sink token. When a token's representation is perturbed, shown in red, the perturbation spreads differently through the network. Without a sink, left, the perturbation affects many tokens across layers. With a sink, right, the perturbation's impact is contained. This control mechanism helps prevent overmixing, a problem where token representations become too similar after passing through many attention layers. Section 3 connects attention sinks to existing mathematical concepts like rank collapse and representational collapse. The authors derive equations showing that sinks control how sensitive one token's representation is to changes in another token. They demonstrate this with GEMMA 7b experiments. When is removed, attention maps become smoother and token representations influence each other more. Interestingly, some attention heads use as a default focus when they don't need to perform a specific operation. Essentially, an if-else mechanism where attending to, which has low norm values, acts as a do-nothing operation. Figure 2 shows empirical evidence for the theoretical claims. The researchers made a small change to a prompt about Shakespeare, replacing greatest writer with best writer. They tracked how this perturbation affects token representations throughout the model. With present left, the perturbation stays relatively contained. Without right, it spreads much more widely through the network. This confirms that attention sinks help control information flow and prevent excessive mixing. The experiment provides a practical demonstration of the mathematical concepts discussed in Section 3. Section 4 examines how different factors affect sink formation. The researchers trained models with identical architecture but different context lengths, finding that longer contexts lead to stronger sinks. They also compared LLaMA 3.1 models of different sizes and found that larger models develop more pronounced sinks. These findings align with their theoretical framework. Longer contexts and deeper models are more prone to overmixing problems, so they naturally develop stronger sink mechanisms to compensate. The progression from 46% sink heads in the 8B model to 78% in the 405B model provides compelling evidence for their hypothesis. Table 2 shows results from experiments on how training setup affects sink behavior. The key finding is that attention sinks form regardless of how is included during training. However, if the model is trained with fixed as the first token, it specifically learns to use as its sink. Removing during inference then causes major performance drops. If trained without a fixed AGI, the model still forms a sink at whatever token appears first. This suggests that sink formation is a fundamental property of transformer training, not just a quirk of specific token choices. This paper provides a new perspective on attention sinks, showing they emerge as a solution to fundamental problems in transformers. By directing attention to the first token, models gain a mechanism to control information mixing and prevent representational collapse. The strength of this mechanism scales with model size and context length, explaining patterns observed across different models. The authors connect several theoretical concepts, rank collapse, representational collapse, oversquashing, to explain this behavior. These insights could guide the development of more efficient transformer architectures that handle these issues more directly.